Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this session we are going to continue our discussion on the energy conservation for multi-particle systems. Okay, so we were discussing certain interesting problems related to the rigid body dynamics of some of the known objects, and we will continue our discussion along those lines. And in this module we will start with one example. Okay, so we are talking, so just to recap, the topic of our discussion is energy conservation for multi-particle system. Okay, so the problem says we have two blocks of masses m and 2m which are connected. So let me write this statement and we'll draw the diagram to help us understand this problem. So these are connected by a light circular light inextensible string which passes over a uniform circular pulley of radius A and mass 4m. Okay, so so the setup is as follows. We have a pulley which is of mass 4m, and connected to the pulley we have two light inextensible strings. So the word light means that there is no weight associated or mass associated with the string. And then we have two objects of mass m and 2m. So the pulley is of mass 4m and the other two objects are mass m and 2m. And we have to find, this question says find the upward acceleration of mass m. Okay, so it's quite intuitive that this is this mass m, being the lighter of the two masses, is going to move up and the heavier mass is going to move down, right? So there are many ways to do this problem. We could possibly approach this problem using the laws of motion, or in this particular setup the easier route is we can use energy conservation, right? So we have to write the total energy of the system, where the system includes this masses m and 2m, and also since we have associated a mass of 4m with the pulley, it's going to contribute to the total energy of the system as well, because when the string is moving with the masses, the pulley is also rotating with along the central axis of its place where it's pinned up, right? So the pulley is also rotating about its central axis. So we can treat the pulley as a uniform circular disc, right? Okay, so we can start writing the total energy of the system. So the kinetic energy is going to be half mv square plus half 2m v square plus half I omega square, right? And we expect that, well, so what is this? This first is the kinetic energy of the lighter mass, the kinetic energy of the heavier mass, and the kinetic energy of the disk. So we see that we need to write the kinetic, to find the kinetic energy of the disk, we need to find what's the moment of inertia. The moment of inertia of the disk is, we know that along the central axis is going to be half times mass of the disk times the radius of the disk square. Now this capital M is 4m, and we see that this is half times 4m times a square, right? So we see that this is 2m a square. Okay, so we see that the kinetic energy is half mv square plus we have, so the total kinetic energy after substituting everything, we are going to get that this is going to be 5 by 2 mv square. Now here we have used the fact that the pulley is rolling. So the pulley is rolling. So what does this mean? The pulley is rolling, that there is no slippage of the string along the pulley, right? So so in other words, technically what it means is that the angular velocity omega is v over a, right? V over a, and we see that if we use this information, I'm going to get the total kinetic energy is 5 by 2 mv square. Okay, so then what we can do is we can possibly keep, we can, let's say we have, we can keep the pulley to be at the 0 level. So we also need to write the potential energy. Remember, the total energy is kinetic energy plus potential energy. So the pulley, we can keep the pulley to be at the energy level 0, the potential energy level to be 0, right? Okay, so then we see that if that's the case, we can also say that at any given point of time, the mass, the larger mass is at a distance z, right? And we see that the smaller mass, so well, we can, well, we need to be slightly careful in this setup here. So let me redraw this this last bit of information. So we have, let's say z, this smaller mass is at a height z, so this is also z, and well, so z is changing, right? So we can keep, well, so here is the issue here. We can keep both the distances as z. So what's the point here? Because z is a variable of the system, z being the vertical distance from the central axis of the pulley. So that is going to change with time. So that's a variable. So to find the total potential energy, the total potential energy is, we have for this lower mass, the smaller mass, we have mgz, and the larger mass is, let's say at any given point of time, is slightly lower than the smaller mass. It's going to be minus 2m gz, right? So this is the larger mass, 2m. So the total mass is minus mgz, right? And we see that that's the total potential energy, and our total energy E is going to be the kinetic energy plus the potential energy, right? And we see that this is the net energy. Now so that's what we have, and this E is going to be the total energy of the system is constant. Okay, so see, the problem asks us to find the acceleration of the smaller mass. So to find the acceleration, we can try and differentiate this identity that we have written. Let's say identity 1. So we differentiate with respect to time. Okay, and we see that this is dE dt, E being constant on one hand, this is going to be 0, and on the other hand it's going to be 5 mv dv dt minus mg dz dt, right? And we see that dz dt is nothing but the velocity v of the system, and we can post process this small equation. We see that dv dt comes out to be g over 5, right? And that is the acceleration that we expect the lighter mass to move up, and that is the same acceleration we expect the heavier mass to go down, right? So because we are talking about the entire system here, so we see that if we use our energy conservation, the problem becomes much easier to tackle with. Otherwise we need to write the various components of the force balance, and that becomes a little bit tricky. So energy conservation is a truly powerful identity. Okay, so then we have another problem, an interesting problem at hand here. So we'll talk about rigid body truly in motion. What do I mean by that? A rigid body which is experiencing both rotation as well as translation. So how to tackle those set of problems? So rigid body in motion. Okay, so rigid body in motion. So suppose we have a system of particles S. So we treat rigid body to be a system of particles, right? So system of particles S, which has a total mass of m, and that its center of mass, the Cm, being g, right? So center of mass being g, right, which has a velocity v, right? And then we have the total kinetic energy. The total kinetic energy of S can be written in the form T given by half mv square plus we have the Tg being the translational kinetic energy of the center of mass, right? So the total kinetic energy is the kinetic energy of the particles about the center of mass and the kinetic energy of the center of mass g. Okay, so where Tg is the kinetic energy of the system of particles S in its relative motion to g. Okay, so typically this half mv square is the translational kinetic. Our notation is exactly the opposite. So half mv square is the translational kinetic energy of the center of mass, and Tg is the kinetic energy with respect to center of mass. So this is the kinetic energy of the center of mass. Okay, so let us look at this setup in a problem, right? We try to understand this setup with a problem. Okay, so we find the kinetic energy of the rolling wheel as shown. Okay. So the problem is as follows, that we have a wheel and the wheel is rolling, right? So we have a wheel and the wheel is rolling, and we have the center of mass C, center of mass of the wheel being C, and of course when it is rolling, it is of course also moving forward with some, let's say, some velocity u. And since it is rolling, let's say its rolling angular velocity is omega, and let us now try to draw some geometry here, try to show the geometry. Let's say at any given point of time, the angular displacement of any given particle on the wheel being theta. So so we have that any particle p has moved by a distance omega theta, right? So that's the length of the sector. And let us say this radius being a, and let's say at any given point of time, at any given point of space on the wheel, the radial distance being rho, right? So the radial distance being rho, right? Okay, so what we have is, and further we say that at any given point of time the wheel is of course touching the base, let's say the floor, and since it is rolling, right? So at let's say its point of touching the floor is capital Q, right? Okay, so then what we have is that the moment of inertia of the disk, in this case the disk is going to be half mv square, half mb square. So that's the MOI of the disk, where half ma square, where a is the radius of the disk, right? And now what we have, since we have rolling, so due to rolling, see, rolling is an important condition. What happens is, when the wheel is rolling rather than slipping, if it is rolling, we expect that at the point of touching the floor, the velocity of the wheel is going to be zero at the point of touching, right? So VQ is 0, right? So then in this case what we have is that our angular velocity omega is going to be, so omega times b is going to be the v, where v is the velocity of the u is the velocity of the center of mass, right? Or the center of the wheel in this case. So what we get is the angular velocity is related to the translational velocity of the wheel, which is omega is u over b. So so that is what we have, right? So we can use all this information to write the total kinetic energy of the wheel. So we see that this is half mu square plus half moment of inertia of the disk ma square and times u over b whole square, right? So we have this as the total kinetic energy. The omega was u over b, and we can process everything. We find that this is equal to 3 by 4 m u square, and that is what we have. Okay, so so that is how we try to solve problems where the body is both rotating and translating. So we use certain conditions in the problem. In this case, the condition was the rolling condition. Okay, so then what we have is, we have another problem, the problem of a wheel rolling through an incline, right? So a uniform hollow, this time not a wheel, but let's say a cylinder, a uniform hollow cylinder is rolling down a rough plane, inclined at an angle alpha with respect to the horizontal. Okay, so we need to find the acceleration. We need to find the acceleration of the cylinder. Okay, so what have we got here is that we have a wheel, not a wheel, but a cylinder which is rolling down a rough incline. So the moment we talk about rough, the word rough should give an indication that there is some sort of a friction which is associated with the surface, which is the inclined surface. So we expect that the wheel is not going to slip, since there is some sort of a roughness associated with the surface. So the cylinder is going down the incline, and we need to find the acceleration of the cylinder. So again, we can approach using the energy conservation, right? So we can try and write down the total energy of the system. So suppose we have that at any given time t, the cylinder has a displacement x along the plane. Okay, so along the plane. So we are saying that let's say the cylinder is moving down with a velocity v, and since its displacement along the plane is x, so v is going to be x dot, right? Rate of displacement along the plane. So then we can expect that, of course, since the cylinder is rolling, why I say rolling? Because the surface is rough. There is some sort of a friction. See, in the problem, we can assume rolling. Why? Because there is roughness associated, and not only that, we are not explicitly mentioning that there is slippage. Had we, if we are not explicitly mentioning slippage, we can peacefully assume that the system is rolling. Because the moment the system is rolling, the number of degrees of freedom, in this case, the angular velocity is going to be known, and the number of degrees of freedom comes down by 1, right? So again, if we can say that the radius of the cylinder is a, so in that case, our angular velocity will be v over a, right? So that is the rolling condition. Okay, so let us continue and complete this statement of our assumptions here. So the cylinder has a displacement x along the plane, and its center of mass g has a velocity, center of mass g has a velocity v, which is x dot, right, down the plane. Okay, and so we have the rolling condition we have already written, and we see that the moment of inertia, since the cylinder is rolling, we also talk about, of course, the rotational kinetic energy, or we have to worry about the moment of inertia. So the moment of inertia of the cylinder in this case will be m a square. This is a hollow cylinder. I think at some point of time we also have to write down the results for the moment of inertia of regular rigid bodies, which we'll shortly introduce. But for the time being, let us just take it for granted that the moment of inertia around of the cylinder about its central axis. What is the central axis? The axis about its center, right? And that is ma square. So now we can write the kinetic energy of the system, which is half mv square plus half I omega square, which is half mv square plus half mb square, ma square, which is the moment of inertia of the cylinder, times v over a, right? So v over a whole square. Okay. So then we can process everything out, and we are going to get that this is mv square. Now, similarly, we can write the potential energy of the cylinder. Remember, our system is cylinder, right? So we have that. So if this distance moved is x, so at any given point of time we can draw the triangle. So if this is x, the perpendicular distance or the vertical distance that the wheel moves is x sine alpha, and hence the potential energy is going to be mg x sine alpha with a minus sign because the distance is going down. So the vertical distance is downward. Okay, so we have this setup, and now we can write the total energy. But before that, we also have to worry about what are the other effects. For example, what are the effects? How does the constraints contribute to the total energy? The constraints. What are the constraints? The constraints are that the wheel is moving on a rough, sorry, not the wheel, but the cylinder is moving on the rough surface, which means that there will be some sort of a normal reaction as well, right? So these are all internal constraints, and we understand due to Newton's third law that these internal constraints are not going to do any additional work on the system, right? So the constraint forces in this case, the normal reaction, are perpendicular to the velocity, right? And we know that the work done is F dot V, and if there is any normal force which is normal to the velocity, the dot product is going to be 0. So do no work, right? So do no work. And so then we can write down the total energy of the system. The total energy is mv square, the kinetic energy, minus mg x sine alpha, right? And we see that we can differentiate. What do we want to find? We want to find the acceleration of the cylinder. We can differentiate this with this whole identity with respect to time, and we know that the total energy is not changing with time, so dE dt will be 0. From there we can find out that our acceleration dV dt of the cylinder comes out to be g by 2 sine alpha. Remember, we have also used the fact that v is x dot. So when we take the derivative, our v is x dot here, right? Okay, so we see that all these complicated problems, when approached with the energy principle in mind, becomes relatively easier to tackle, right? So let us look at another problem in 3D in statics. In this case, we'll just restrict our statics to 2D, but we'll see how complicated the problem is in 2 dimensions and how simple it becomes when we take into account the energy conservation principle. Okay, so what we have is we have the case of the example of the sliding ladder. The sliding ladder. Okay. So we have the ladder which is sliding down, of course, on a the ladder is kept on inclined on a wall, and the wall is sliding down, and what we have is, let's say this is my ladder, and the ladder is of course homogeneous. We can consider ladder as a stick because we are talking about a problem in 2D, right? So well, let me write down the problem and all the details will be clearer then. So a uniform ladder of length 2a is supported by a smooth horizontal floor, right? So a uniform ladder of length 2a is supported by a smooth horizontal floor, and it leans against a vertical wall, right? A vertical wall, and it makes an angle of 60 degrees. So what I'm talking about is this angle is 60 degrees, right? And then we want, well, with respect to, let me just clarify the problem further with respect to vertical, right? Okay. So then we want to find the energy conservation equation for the ladder. Okay. So well, see, notice the word smooth here. The floor of the ladder, the floor on which the ladder is kept is smooth. So we expect the ladder to slip, right? The moment there is no roughness, the ladder is going to go down. It's going to slip through the floor, and we expect, so the implication of this statement is we expect that theta is going to change. So theta will be theta of t, where theta at t equal to 0 is 60 degrees, right? That is the initial condition. Now we expect the ladder to always stay in touch with the wall as well as the floor, because that becomes very strange if the ladder leaves the wall, and then the problem will not be dealt with statics in that case. So we expect the ladder to be staying in touch with the wall and the floor, and if that is the case, the ladder is of fixed length 2a. Since the ladder is of fixed length, the only variable, the only degree of freedom is theta, right? So there is, so that's the important point to note. So there is only one degree of freedom, which is theta of t. One degree of freedom, which is theta of t. Okay, so then what we have is, that so let me also try to introduce some more variables in the problem so that the problem is easier to tackle. Let us say we are talking in 2D here. So our horizontal axis is the x-axis, and our vertical axis is the z-axis. So let's say the center of the ladder, since it's a homogeneous ladder, the center also is the center of mass of the ladder, right? So the center of mass of the ladder will have a coordinate x comma z. So x comma z is the coordinate of the center of mass g of the ladder, right? And what we have is that x is a sine theta and y is z is a cos theta, where theta is this angle with the vertical, right? So a cos theta and a sine theta. Okay, so that is what we have, and now we can write down the velocity, the respective velocity of the components. So x dot is a sine theta times theta dot, and y dot is a cos theta times, well, a, something is wrong here. So x dot is a cos theta dot, and y dot is not y dot. Z dot is a sine theta dot, and with a minus sign. Okay, and now we can write down the at least the total kinetic energy of the system. So we have the kinetic energy of the system is half m being the mass of the ladder. Have we introduced mass? Let's say m is the mass of the ladder. So m is the mass of the ladder. Okay, so half m x dot square plus y dot square plus half il theta dot square, right? So what we have is that il being the moment of inertia of the ladder here. So we can say that this ladder we can treat ladder as a stick, right? And the moment of inertia of a stick about its center will be what? Will be equal to m by 3 a square. A being the semi length of the ladder. Okay, so then we can substitute everything. See, theta dot. So when we substitute everything, all these details, we find that the total kinetic energy comes out to be 2 by 3 m a square times theta dot square. Okay. So then what we have is, how about the potential energy? The potential energy will be, the ladder is slipping and its center of mass is going down. How much down? It is going down by a distance z, right? So we have that the potential energy is going to be mg z. So z is mg a cos theta, right? And we can always put a minus sign because the potential energy of the system is going down, or we may not, because all the sign conventions will be automatically taken care of, because we are dealing with a variable theta here, or we are dealing with a variable z. So z will inherently, sometimes the math takes care of the sign conventions themselves, right? As we shall see. So, so this is the total potential energy, the total kinetic energy. So the total energy of the system is ma square by 2 by 3 ma square theta dot square plus mga cos theta. So that is the total energy of the system, and I think that is what we want. For the ladder. Now there is one problem with this setup. We don't know what is E. So what is this E? So to find what is this E, we need to look at what is the initial condition of the setup, and from there we can find this constant E. So the initial conditions being, at t equal to 0, we have that v, the velocity of the ladder is 0 and theta is 60 degrees. So we can plug everything. So when v is 0, we have that theta dot is 0 and cos theta is 60, being cos theta is half. So we see that the total energy of the system is mga by 2, because cos theta is half, and then that is what we plug it here, and that will bring us the energy conservation of the setup. Okay, so so that we wrap up this discussion at this point of time, and in the next module we will talk about the linear momentum conservation for the system of particles or for rigid bodies. Thank you so far for listening.